Okay. Well, so hi all. I'm going to be talking about a tool called the Planetary Spectrum Generator that we released recently. We've been working for many years on this, and you may find it of interest. So the generator is an online tool, but actually it's also a set of write and infer packages. So the idea is that you define the target you want to observe. Let's say you want to do an exoplanet, the atmosphere of the exoplanet, and the instrument you want to use, and it will give you a spectra. You can do transit, coronagraphy, and it can also run it. This is the web interface, but it can also run it from your own machine with your own Python scripting, and it can also install it in your own machine. The package is pretty big, so it's difficult to install it in your machine, but we found a way in the last weeks to maybe be able to, you can actually put it in your machine. So the paper was published, it was in May 2018, so very recently. I've been working on this for the last 2 years mainly, and some of the applications that people have already been using this. So it's the official retrieval for the ExoMars TGO mission, it's for JameSwep, the Solar System GTO, the LUVAR, OST is being used by Ariel and Outlier First, but it's in the component of an RCRTF. It's used for carbon monitors. It's being used in a lot of mission development, and recently we're playing with Google and to do millions of spectra, and it's being used by a lot of people. So it's a lot of versatility, and I'm going to be talking mainly about the exoplanet use of this tool. So this is just a picture I took this morning. So there are roughly 10,000 hits a day, and these are not robots or crawlers. These are people actually running this stuff. And most of the work is done actually to do Earth sciences. They do a lot of modeling for Earth, but people use it for many different things that are unthinkable. Some people in Japan contact me that trying to measure magnetic fields on the sun, and they want to use it for balloon. I know. So people use it for very different aspects. So it's very, very, very versatile too. So what is this thing? So what we did is we combine the main molecular repositories out there. So it's Hydran, JPL, MolSpec, CDMS, non-LT fluorescence codes. We homogenize and put them in. Then we put a lot of the output constants from from different databases, USGS, Ames, Lowell, and then we also put them in, homogenize and clean them up. Then we also integrate a lot of GCM models especially for Mars, and also include some basic equilibrium chemistry for exoplanets and also some orbital calculators into this. And then we also combine instrument models. So the idea of normally when you run a write and infer calculation, you tend to have one of these things, but you lack the other ones. So the idea to put them all together is to make this more cohesive. And the good thing about this is that it grows naturally. So if you improve something for Mars, the applicability for exoplanets is direct. And this is on a web server. So we put this in supercomputers at NASA Goddard, and we have a web interface that this is the thing you were seeing before. So this is just to give you a sense what is included. So these are the databases that go inside, the full Hydron database, which is a molecular database. There are in total more than 1,000 type of molecules inside, line list for different isotopes, non-LT, GEISA, JPL, CDMS. So it uses almost all the latest one, also UV spectroscopy. And these are some of the ones for surface components. I don't know if you never dealt with this, but I have to say this is very like a very cottage industry, and people have different ways to quantify this stuff. So it took me a long time to homogenize, clean them up, the different sources, so they actually are practical for astronomy or measuring exoplanets or planets in the solar system. So what it can do, it can measure, you can do UV calculations from the 10 nanometers to 100 millimeters. So you can do every spectral range. You can simulate from almost any observatory and any lander. And it has the main neat thing about this, it has a 3D calculator for almost anybody in the solar system and all confirmed exoplanets. So I will show you, it will actually does a 3D calculation, which are essential for any write infer calculation. Then it does line by line, correlated K, multiple scattering, and non-LT calculations, and surface model. So this is what is the main core. And these things, even though they're very complicated, I didn't invent this. These are 70 years old techniques that have been there, and the idea was to put them in a package that are there. So the main things about this is to gel a lot of the knowledge that was out there into a tool. And includes, and the neat thing is also include noise simulators for a lot of spacecraft out there, observatories. And I will show you a little bit about that, interferometers and coronagraphs too. So these are, as you've seen this plot before, so these are the components that are going into the write and infer. And all these things, all these elements are actually included per se in the code. So for exoplanets, that's a line by line. If you do very high res resolution spectroscopy, we'll also do correlated K for model resolutions. It does full scattering. You can define the complexity of your scattering calculation, but it does full scattering with many legendary polynomials. That's Rayleigh, obviously, collision-induced absorption, and the UV also, and it does a layer by layer in spherical geometry. This is for comets that you don't care about here, but this is for surface. So if you're doing bodies that have a surface, also the modeling of the surface, the scattering on the surface is relevant, and this one will also do. Most of the people that I know work with this thing. They use it for studying icy bodies like, I know, Pluto or Europa, so they can model the surface of the body with this Hapke model. And the neat thing was this thing about the instrument models. Actually, you can pretty much characterize every telescope out there with a, in general concept, with a limited amount of parameter space. So we have a very generalized noise model that took us actually a long time to develop, but it's very, very versatile. And what we have done is we went to almost any observatory there and collected all the parameters about the optics, the thermal properties, the spectral properties, and the detector properties. So then you can say, I want to do James Webb NIRSPEC, or you want to do Keck NIRSPEC 2, or you can do HST, and then it will model the noise component and the performance of the thing. So this is just to give you a sense what simulation looked like. This is a simulation of Jupiter, Neptune. We did a UV transit on Exoplanet, Pluto, Super Earth, James Webb, or LUVOIR, Earth-like planets. These things actually are run on the server, and these are most of the thing has been benchmarking. These figures actually, if you compare to the original papers, the match is remarkable. So the idea was to first benchmark all the right transfer packages, so then you can adapt it and make it versatile for what you want to do. You can also do retrievals. I use it for my own retrievals. This is a retrieval for HDO on Mars, and also being used for the ExoMars mission. And this is if you want to do comets. And the key thing is you can also run this with your own machine. So you can have your own Python scripting. You send a command to the supercomputer with a very simple file, and then it will run any of these models, and it will give you back spectra. So it's very versatile. And if you want to run a lot of calculations, the supercomputer will kick you out. Actually, I'm restricting to 1,000 computations per day because I was getting too many calculations and it was getting expensive. So I implemented recently this. It's still in beta mode, but I think it's working well. It's called, you can install a virtual machine in your machine with a Docker container. I don't know if you heard about it. And it's pretty simple to do. So you can just pull it, run it, and you have your own web server in your machine to do the PSG calculations. So, and I will do a little demo. This is risky. This is a Windows machine, and I feel like it may not work, but we'll see. So you go to this website, PSG. You can actually run it from your cell phone. Actually, you can even run the calculation from a cell phone. I've been running, you can test things. So the easy thing you can do is always look for a template. So let's give an example. You pick an exotransit from James Webb. You do load. And then it will define the geometry for this transit, the atmosphere, and then you press generate spectra. So that will be the first step to see what it did. Okay. So you see in 1 second, it did a 3D geometry calculation. It did the full layer by layer correlated K calculation, and it give you also the noise performance. You can download this and the radiances. This is the transit for this thing. And also tells you the transmittance, and also tells you where the noise are. You can see the noise being defined by the source, or you can also know how to improve your measurement to know where are the source components. And this is not a precise James Webb simulator, but it gives you a pretty accurate representation if you put the right integration times. And the neat things are things like this. So if you pick an exoplanet here, GJ, for some of this guy, and then we do now. It does so that did a 3D calculation of the geometry out there, and it shows you that planet is looking like this. It's already here. It tells you all the parameters about the exoplanet, the phase, and how it looks like. And then if you do T, it will calculate the next transit, which is at 1032, and it shows you here where the planet looks like, the impact parameter, and all like that. Based on this information, also it knows about the gravity, density, and all that. It will use a simple equilibrium chemistry model, and it will give you some a prioris. You can modify them, but it will tell you the temperature profile of the exoplanet, and it has all the exoplanets, so you can actually do all of this for any exoplanet. And also using this PT profile based on Parmentier model, it will also compute equilibrium chemistry for you. Just these are prioris. You can modify them, you can put on your profiles. But it's, if you don't know anything about the exoplanet, you just go put the exoplanet, and it will give you a priori all this information. And that's kind of the big thing. So then you can say, well, I want to modify a little bit this. You can say, let's modify, I don't know, these are the different equilibrium chemistry. You can say, let's do more one times solar, and then you get the new chemistry for the exoplanet. So it's very, very fast. And this is already done on the server. And then you can come here. This is for the atmosphere of the planet. And then you can come here and then define the instrument you want to use. You can say, I want to use James Webb. I want to use, I don't know, MIRI. And then it will load all the parameters of the MIRI spectrography, and you can run simulations. So it's pretty straightforward, has been benchmarked, so it should be pretty easy. You can use any unit you want from the output. You can use watts, Genskis, or any desired quantity, contrast, which is neat. And then I give you, for example, I would do a coronagraph, which are very complicated. So if you do LUVOIR coronagraphy, so this is a Earth-like planet with coronagraphy observed with LUVOIR. And so this is so it show you how the planet looks like. So this is the stellar spectrum being suppressed by 10 to the 10. And then on top of that, you get the planetary spectra here in blue. And it show you where the components are. So most of this stuff is water. You can actually disable or plot stuff. You can download the stuff here. It's pretty, this is the data. You can actually download it for you. And also tells you where the noise performance. You can see that because it's kind of a relatively warm, optimized for UV, up to above 2 microns, you start to get a lot of background contamination, background thermal contamination. So, if you want to do, for example, just to play with this, and I'm about to finish here, and then you just say, I want to make it cooler, LUVOIR, just to see how it looks like. So you say the temperature of the LUVOIR is 1 Kelvin. And I've actually been fighting for that, but I've not been successful. But if you cool it to 1 Kelvin, for example, you have a cooler LUVOIR, and then the measurement will look like. So now your noise drops substantially over there, and your noise, you're defined now by the source. You're no longer defined by the background. So this is you can play with this. You can download it, and I try to put a lot of information on the system here. So if you go up here, there are a lot of tutorials, how to initialize the thing, and explain you what all the parameters are. There are some videos here you can also play. And then the last thing is, people ask me all the time, what are the units you use for all this stuff? Here they explain how to download it, and then every unit for every parameter explained here tells you all these things. And that's all. Thank you.
So we have time for one question. Anyone?
Well, I have a short thing. Thank you. This is awesome.
Please.